So this is the second video in sort of a two-part series looking at some numerical simulations of a passive neuronal membrane. And in the previous video, we looked at simple current injections that sort of look like this, just a simple current step. And in this video, I want to look at two different kinds of inputs. The first is a sinusoidal input, like this one here. And after that, we'll move on to injecting noisy inputs. So in this simple case, you have a sinusoidal input, and you can see that the frequency of your input is equal to the frequency of your output. So remember, the output is the membrane potential of the neuron, and the input here is the injected current. So, okay, that's nice. Well, are these two traces exactly identical is the next question. And it might be somewhat difficult to see, but I hope that if you look at this closely, you can convince yourself that there is a delay in this system here. There's a delay between what the command steady state voltage is and what the actual membrane potential is. And you know that has to be the case because of the time constant of the membrane that we've been talking about. So if you look at the end here, the actual membrane potential is sitting, somewhat towards the lower part of its trajectory, whereas the red input current is almost halfway up to its peak. So if you look at just the end points here, you can see that the red injected current is actually leading the membrane potential, which is sort of trailing because of the time constant. And you can think about this as, if you overlaid these two plots, the injected current or the steady state membrane potential, however you want to think about it, is going to look, essentially identical to this sinusoid, except it'll have a phase delay. And you can actually calculate this phase delay, which we normally denote as phi. And I'll provide a reference where you can actually, you can do some math to actually calculate how large the phase delay actually is. And now let's look at what happens when we inject a sinusoidal current at a higher frequency. So this is the previous example simulation that I was showing you, and now I've given you a second example where I've increased the frequency of this input many-fold. And what I want you to realize is that for a higher frequency input, the amplitude of this sine wave is much less. So from here it's going from roughly negative 57 to negative 62 millivolts, if you can read the Y scale here. Whereas here it's got a much larger amplitude from roughly negative 50, or a little bit more than negative 50 to a little bit less than negative 70 millivolts. So for a higher frequency input, the amplitude of your voltage oscillations decreases. And if you think about this for a little bit, this sort of makes sense because, as I said before, the membrane potential is trying to follow the injected current, but if the injected current is moving really quickly, the membrane potential won't be able to keep up because of the fixed time constant, or the delay that is built into the system. So if you think about that, that should hopefully make sense to you. And you can think about a current that, if you continue this and inject current with an even higher frequency, and then an even higher frequency, until you get a current that's an infinitely quickly oscillating frequency, the membrane potential would actually just be flat at resting membrane potential, because the steady state membrane potential is oscillating so quickly above and below it that the membrane potential just simply cannot keep up at all. And it, for one moment in time it wants to increase, but in the very next moment of time it wants to decrease. And these increasing and decreasing impulses essentially average out, and you get a membrane potential that just simply doesn't respond at all. So if you think about what this means, what this essentially means is that the membrane potential will selectively respond to lower frequency input, or it will respond with a greater amplitude to frequencies that are slower. So if you look at the injected current here, I've just increased the frequency. The amount of current that I'm injecting, the amount of nanoamps I'm injecting, is actually the same, but the membrane potential responds with a greater amplitude to this lower frequency input. And what this means is that the membrane potential can be thought about as a low-pass filter. or at least a passive membrane, works as a low-pass filter. And this is just some fancy terminology to say that low frequencies or low-frequency input passes through the filter, or is selectively responded to at a higher amplitude, whereas a high-frequency input is diminished or sort of washed out. Okay. Sorry for the bad handwriting there. I was just trying to write that quickly. So this leads us into thinking about what happens when you inject a noisy input into the cell. So here I've injected a white noise input, and you can see that my noisy input has basically very high frequencies in it, and the definition of white noise is that all possible frequencies are sort of equally represented within this trace. And if you look at the output, the membrane potential, it is sort of a filtered version of this input, and that's sort of why we use the terminology of a filter. So the output, again, you don't see as much of these like very quick frequency inputs or high frequency oscillations, and you rather see the expression of these somewhat slower these oscillations or deflections that occur on a slower time scale. So this is what happens when you inject a white noise input, and if you think about this sort of falls out of the fact that of what we were talking about with just a simple sinusoidal input, that the membrane potential is preferentially responding to low frequency features of the injected current input. So it turns out that you can actually mathematically figure out what frequencies are expressed in any given signal. And this is what I'm plotting on the right. This is this same trace in the frequency domain, or sort of after a Fourier transform. So the Fourier transform, for those of you who don't have as much of a math background, I will post some references if you're interested in this. But essentially all I want to do is just show what I've already told you in words. So on this x-axis, these are this is essentially you can think of this as the amount of low frequency signals or low frequency components of this signal, and on the top here, these are the high frequency components of that signal. And you can see that in the case of the membrane potential, you get this diminishing effect, or a diminishing amount of high frequencies. So, and this cutoff is quite drastic. Whereas in the input signal here, you have essentially, I mean, it's noisy, right? But if you just take the average, it's a flat distribution, and that's actually what the definition of white noise is. That this distribution of frequencies is flat, so all frequencies are equally represented by. All frequencies are equally represented within this white noise input. So this is a little bit of an advanced concept for those of you who who don't have the math background, but this is just showing what I've already told you in words. Okay, and then the last simulation I just want to show you very quickly is what happens when you inject a different noisy input. So this noisy input here is called pink noise versus white noise, and there's all different kinds of or colors of noise. There's red noise and other noisy inputs. And what pink noise essentially means is that the frequency distribution in this Fourier domain I've been talking about falls off with according to 1 over f. So where f is the frequency. So high frequencies, as frequency increases, then the amount of that frequency, or the power, the spectral power, decreases. And if you inject a current, pink noise current, what happens? Well, you can again see that the high frequency components of this input are completely lost in the membrane potential here. So, and if you look at the amount of frequency in the membrane potential, it drops off more steeply than the amount of frequency in the input. So this is just another example that is essentially showing you the same thing. And if you download the code, you'll be able to inject pink noise of different amplitudes. So you could increase the amount of amplitude here, and you can inject white noise, you can inject sinusoidal currents of different frequencies and amplitudes. So if you play around with this enough, you will begin to sort of understand and develop an intuition about what a passive membrane does. And that's actually, I think, a very important it's a very important baseline for understanding what we're going to be talking about later. So I've already gone very long in this video, so I hope that you gained some intuition, and if you want to learn more, you should download the code and learn Python. Thanks.